So today this will be lesson 6. This is going to involve logarithmic and exponential equations. This comes from chapter 6, section 6. So as we build on to our topics, we should be a little bit more familiar with an exponential function. We've been working with logarithms and we're starting to get familiar with the properties of logarithms. So always have those properties of logarithms handy. They'll be very helpful. So in this lesson, we're going to work with logarithmic equations and exponential equations and develop strategies to solve those types of equations. So the first type of logarithmic equation, if the log is on one side, then what we can do is rewrite it using what's called the exponential form of the equation, if possible. So let's have this example. We have the log of 1 minus 2x base 3 is equal to 2. What we pick up on is, in this problem, we can put this in exponential form. So this can become then 3 squared is equal to 1 minus 2x. So remember, the base is 3, the 2 is the exponent, so they become one side of the equation. The 1 minus 2x becomes the other. So 3 squared is then 9. So now we have this 9 equals 1 minus 2x. And again, I like to have the variable on the left side. So I'm going to write this as 1 minus 2x equals 9. So then if we subtract 1 on both sides, we get negative 2x equals 8. If we divide both sides by negative 2, we get x equals negative 4. And that will be the solution to this equation. The other type of equation is if there's a log on both sides of the equation, then we have to have, and if the base is the same, then we can solve it using this property here. So if we have the log of m base a equals the log of n base a, we pick up on that we can actually just set what we're taking the log of equal to each other. So if I have the log of x base 5 equals the log of 36 base 5, notice that we have the same log on each side of the equation. So what I can do is set m equal to n. But before I do that, though, this 2 has got to be brought back in as an exponent. So this becomes then the log of x squared base 5 is equal to the log of 36 base 5. So we can set x squared equal to 36. And we can take the square root of each side, and that x equals then plus or minus 6. But remember, we cannot take the log of a negative number. X has got to be greater than 0. So we actually have just x equals 6 as a solution. We have to reject the negative because we can't take the log of a negative value based on our domain restriction. Remember, the domain of a logarithmic is greater than 0 if it's not been shifted anywhere. So sometimes the logarithmic equation has a domain restriction, as we were just kind of mentioning. So we do want to determine the domain restriction before solving this equation. So as I said, if I give you y equals the log of x base a, its restriction is x is greater than 0. So what we're taking the log of has to represent a positive value. So to find the domain restriction, or the domain, what we do is we just set the x plus 6 to greater than 0. If we solve for x, we get x is greater than negative 6. And then we also set this x minus 2 greater than 0. We get x is greater than 2. So what we can do is put these both on our number line, and our domain ends up being the one that's the most restrictive. So the negative 6 would be over here. The 2 would be over here. So it has to be greater than negative 6. So we don't include the negative 6. It also has to be greater than 2. The one that's most restrictive is the one that's greater than 2. So that's where they actually overlap. So the intersection is actually our domain restriction. So our domain is actually going to be greater than 2. So x becomes then greater than 2. If we're using set biddle notation, we would then just say the set of x's such that x is greater than 2. So now we want to try to figure out how in the world to solve this logarithmic equation. So one of the things is, since this is addition, I can rewrite this as a single logarithm. This becomes, if we have a sum, we can rewrite it as a product of the two things we're taking a log of, since the bases are the same there. So this is going to turn into the log of, and let me make myself some more room here. I may have to require a lot of space, so let's slide this over to the far left. So this becomes then the log of x plus 6 times x minus 2 base 5 is equal to then 1. So notice how we have a log on one side of the equation. So I can put this in logarithmic form. So the 5 to the 1 becomes an exponent. The 5 and 1 become one side of the equation. I'm going to make it the right side of the equation this time. So I'm going to write this as x plus 6 times x minus 2. And I'm going to put the 5 to the 1 on their side of the equation. So remember, the base and the exponent go together to make one side of the equation, which leaves us this x plus 6 times this x minus 2. Now 5 to 1 is just 5. So since this is not 0 on the right-hand side, this quadratic's got to get rebuilt. So we got to multiply it all back out and then set it back to 0. So using FOIL, we have x squared, and then we're going to have this negative 2x and the 6x, negative 2x and 6x becomes then this 4x. And then 6 times negative 2 would be negative 12. And that's going to equal then just 5. And then to solve a quadratic, it must be set to 0. X squared plus 4x minus 17 is equal to 0. So we want to try to use factoring, but I don't see the factors of a negative 17 that are going to add up to give me this 4. So the quadratic formula has to be used to solve this. So the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So note that the a is equal to 1, the b is equal to 4, and the c is equal to negative 17. So we want to put those into our formula. So this is going to be x equals the opposite of b, so that's going to be a negative 4, plus or minus the square root of. So b squared is 4, 4 squared is 16, minus 10, and we have to multiply 4 times 1 times negative 17. So 4 times 1 is 4. 17 times 4 would be 68. 4 times 7 is 28. Carry my 2. 4 times 1 is 68. So that's actually going to be a negative 68. And since there's a subtraction sign there, that becomes a plus 68. All over 2 times 1, which is 2. So then we see that this becomes then x equals negative 4 plus or minus the square root of 84 over 2. Now remember, we're supposed to pull out the perfect square inside the radical if there's one existing. So remember, as far as the perfect squares go, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. That's probably enough because 84 is not that big of a number, so it's not going to have a very big factor. So what I'm trying to figure out is 4, 9, 16, 25, or 36, can they divide into evenly 84? It looks like the 4 goes into 84 21 times. So this turns into, we're going to slide over a little bit, go out a little bit further. X equals then negative 4 plus or minus, and this turns into 4 times 21 over 2. The 4 then I can take the square root of 4 using the rules with exponents and radicals. So this turns into negative 4 plus or minus 2 square root of 21 all over 2. So then we have -4. We have to separate this as two separate fractions. So -4/2 plus or minus 2 squared root of 21/2. So this then it turns into -2 plus or minus the square root of 21. So the square root of 21 is a little bit over 4, because I know that 16 or 4 times 4 is 16. So that's going to be over 4. And we know the square root of 25 is 5. So that's that number. So if I go -2 plus something around 4, that's going to be a positive value. And it's going to be, it's still going to be bigger than 2. So it's going to be okay. But notice if I have a negative minus negative, that's not going to be greater than 2. So because of the domain restriction, we're seeing the only answer is going to be is -2 plus or minus the square root of 21. I'm sorry, we're going to throw away the subtraction part. This is going to just be -2 plus the square root of 21. So that becomes our solution. So -2 plus the square root of 21. So we can't forget about the domain restriction in the problem either. So if I want to solve ln of x is equal to the ln of x plus 6 minus the ln of x minus 4, again, the first thing we got to do is note the domain restriction. So the domain, what we got to do is just set what we're taking the log of to greater than 0. So x is greater than 0. X plus 6 has to be greater than 0, which means x has got to be greater than -6. And x minus 4 has got to be greater than 0. So that means x has got to be greater than 4. So I have to choose the most restrictive. So if I look at that on a number line, so we have -6 here, 0, and 4. Greater than -6 would be to the right of -6. Greater than 0 means to the right of 0. And greater than 4 means to the right of 4. So notice that greater 4 is where they all overlap. So my domain becomes then the set of x's such that x is greater than 4. That's the most restrictive domain. So we can't go left of 4, because if we do, then we're going to, this one here is going to be a negative value. We can't take the log of a negative value. So as we move forward, if I have to solve this, what I see is this left side can be written as 1 logarithm. Since this is subtraction, I can use that as a quotient. So when I'm solving this, I'm going to move over to the left a little bit. So the natural log of x is going to equal then the natural log of, and then I can write that as a quotient, x plus 6 over x minus 4. So we have that. Now, since we have the natural log on both sides, all we got to do is set what we're taking the natural log equal to each other. So the m and the n. So this allows me to write this as x equals x plus 6 over x minus 4. Note that there is a domain restriction. You cannot have 0 in the denominator there. So notice that x cannot equal 4. But that's already excluded in our domain anyway. So we don't have to add anything extra to our domain because of that. Now to solve a rational equation, remember we do not want fractions. So we can multiply by the denominator on each side to get rid of fractions. So that's going to be x times x minus 4 over here. And then I'll multiply the other side by x minus 4. The x minus 4 is divided out. And that leaves me x plus 6. So then we have x squared minus 4x equals x plus 6. What we got to do now is recognize, well, what kind of equation do we have? Well, since x squared is present, this is quadratic. If it's quadratic, we want to set one side to 0. So we subtract an x on each side and subtract a 6 on both sides. So our new equation is going to be x squared minus 5x minus 6 is equal to 0. So our next step is, can we factor x squared minus 5x minus 6? It does look factorable this time. So we know that we're going to have x times x here. And the factors of a -6 that give me a -5 would be, looks like a -6 and a +1. So -6 times the 1 does give me my -6, and -6 plus 1 does give me my -5x. So that should work out. So now I can just solve each one for x. So the 0 here would be x equals 6. The 0 here would be x equals -1. So that would be my two solutions. But reverting back to our domain restriction, our domain said it had to be greater than 4. So we cannot include -1 as a solution. So answer ends up being just x equals 6 as a solution. So solving exponential equations with different bases. So far we've had exponential equations with the same basis for the most part. But when the bases cannot be written the same, the strategy is to take the natural log of each side. So that's actually on our calculator, and I think that's the one the book wants us to use is the natural log. The natural log can be used along with the properties of logarithms to solve for x. So we're going to, again, don't forget about the properties of logarithms once we introduce it into the problem. So again, natural log is used, and an approximation can be figured out if I'm using the TI-84 calculator. So if I want to solve 2 to the x equals 10, notice that we do not have the same bases, the 2 and the 10, and that there's no way I can change 10 to a base of 2 because there's nothing 2 to any power that I can see right off the bat that's going to give me 10. So what we're allowed to do, though, is we're allowed to take the natural log of each side. Because remember, what you do to one side, you have to do the other side. So if I take the natural log of both sides, it's still going to be an equivalent statement. So this problem turns into this problem. So what happens is x becomes then an exponent. But since I'm doing logs, we know that the property of logarithm says the exponent can become a coefficient. So I have x times then the natural log of 2 is equal to the natural log of 10. Now I can solve this by dividing both sides by the natural log of 2. So x equals the natural log of 10 divided by the natural log of 2. Now remember, you cannot use the quotient here because this is not one log as a quotient. If it was one log as a quotient, you could write a subtraction, but since it's two separate logs, we have to leave it in that form. If you want the exact answer, if that is the exact answer, but if you needed a decimal answer, you could enter that into the calculator and get a decimal. So let's look at this next example. The first thing I want to do to solve this for x is to get rid of this 5. So I'm going to divide both sides by 5. So this becomes 2 to the 3x equals 8/5. Now, the 2 and the 8/5 are not the same bases. So our strategy is, let's take the natural log of each side because logarithms have special properties that we can use to solve this problem. So the natural log of 2 to the 3x equals now the natural log of 8/5. What happens is the 3x can now come out in front. What I'm going to do is just rewrite this as 3 ln of 2, and I'm going to put the x on the other side. Since that's all multiplication, I like to have the x on the end. Over here, notice that since we have a quotient, I can write that as a separate, using the property of logarithms, I can write that as a subtraction, a difference. So I can write that as the natural log of 8 minus the natural log of 5. Now to solve for x, I just got to divide both sides by 3, the natural log of 2. So if I do that, this becomes then the natural log of 8 minus the natural log of 5 over 3 times the natural log of 2. So I don't really see that simplifying any further, so I would leave that as our answer. If you needed a decimal answer, you could put that into the calculator to get a decimal answer. So if we want to solve some more problems, so if we have 1/2 times the log of x base 7 equals 3 log of 2 base 7, one of the first things to recognize is the bases are the same. What I can also do is I can bring these coefficients back in as exponents. So I can write this as the log of x to the 1/2 base 7 equals log of 2 base 7, but this 2 is now raised to the 3rd power. And since we have we're taking the log of the same, since we're taking the log with the same base on each side, since the bases are the same, we can just set the m and n equal to each other. In other words, I can set the x to the 1/2 equal to 2 to the 3rd. Now, to get rid of an exponent of 1/2, what I need to do is make that turn into a 1. And we know that the power rule says if you raise a power to a power, you're multiplying. I can multiply a 1/2 by its reciprocal, and that make it turn into a 1. So if I square that side, I'd also have to square this side here. So we know that 1/2 to the power of 2 becomes an x to the power of 1, which means I just have an x. This becomes then 2 to the power of 6. So we've learned that 2 to the power of 5 is 32. So 2 to the power of 6 must be then 64. So I don't know if my lab keeps it as 2 to the 6 or if they just change it to 64. I think 64 would probably be the better answer there. So if I look at this next example, I have 2 to the log of x minus 5 base 6 plus the log of 9 base 6 equals 2. Remember, there is a domain restriction. Notice that we have to have x has to actually be greater than 5 because there's that translation there in the graph. So remember, we can see that there pretty easily. Since x minus 5 has got to be greater than 0, x has got to be greater than 5. We can pick up on that because if you pick 5, it's going to make it a 0. If you pick something less than 5, that's going to make it negative. We don't want that. So the next thing I can pick up on is I can bring this 2 back in as an exponent. So this becomes, and I'm going to move over a little bit to give myself some room. So this is going to become the log of x minus 5 squared base 6 plus then the log of 9 base 6 is equal to 2. Now, since these have the same base, I can connect this back as a product. So I can write this now as the log of 9 times x minus 5 squared base 6 is equal to 2. From there, I can write this in exponential form. So this becomes then, and I'm going to keep the 9x minus 5 squared on one side. So this becomes 9 times x minus 5 squared on one side. And that 6 to the 2 becomes their side, which is 36. So I have 9 times x minus 5 squared equals 36. What I'm going to do here is, since x minus 5 is squared, I'm going to show you a little shortcut on this. Is just go ahead and get rid of the 9 to start with. So this is going to become then x minus 5 squared. And this is going to equal then 36 over 9. Like that. And what I can do now to get rid of the power 2 is I can take the square root of both sides. By doing so, this becomes then x minus 5 equals a plus or minus, and the square 36 would be 6, and the square 9 would be 3. I guess I should want to simplify that. Hold on here. I didn't realize, yeah, 36 divided by 9 is actually 4, isn't it? So let's just make that even easier. So when I divide by 9, 36 divided by 9 would actually just be 4. So now if I take the square root of both sides, we're going to have then x minus 5 is equal to a plus or minus 2. So if I add 5 to both sides, I have x equals now 5 plus or minus 2. So that means 5 plus 2 is going to be 7, and 5 minus 2 is going to be 3. But since our domain is x is greater than 5, we have to throw out the 3. So answer x equals 7 would be our solution. So this one right here, what I can do is I could probably move this log to the other side since they're the same bases. So this becomes then, I'm going to give myself some room again. This becomes the log of, I also need to do domain restriction, so let me do that as well. So this is going to become the log of 7x plus 6 minus the log of x minus 1 is going to equal then 1. So I could get the logs on the same side of the equation. Let me go ahead and do that domain restriction. So 7x plus 6 must be greater than 0. So x must be greater than negative 6/7. And the other one is x has to be greater than 1. the most restrictive is the x is greater than 1. So our domain becomes then x is greater than 1 because it's the most restrictive. So if we put that on a number line, you would see that 1 would be the one that's most restrictive. So since we have subtraction over here, we can write this as a quotient. So this becomes the log of 7x plus 6 over x minus 1. And that's going to equal 1. Now, since we have a log on one side, we can write this in exponential form. And remember, the base is a 10. So 10 to the 1 is actually 10. So I'm going to have, we'll make some room again, 7x plus 6 over x minus 1. And that's going to equal 10 to the 1, which is actually 10. Because you understood there's a little base of 10 there. So 10 to the 1 gives me 10. So that becomes one side of the equation. I like to have my variable on the left side, so I'm just swapping those. Since we have a rational equation, notice how we have a domain restriction. X cannot equal 1, but notice how we already got it restricted out of the domain anyway. So what I need to do next is multiply each side by x minus 1 to get rid of the fraction. So this turns into 7x plus 6 equals 10 times x minus 1. So to solve that equation, it looks linear. So I'm going to simplify the right-hand side. So it's going to be 7x plus 6 equals 10x minus 10. So again, to solve a linear equation, I always like to pick on the little guy. So the 7x is going to go off, subtract 7x on both sides. That's going to give me 6 equals 3x minus 10. Then we're going to move the 10 over. That's going to be 16 equals 3x. We're going to divide each side by 3. So it's going to give me 16 thirds equals x. And again, 16 divided by 3 would be 5 something. So that is in our domain, so we don't have to reject it. So that would be our solution since it doesn't reduce. So number 4, we have the natural log of x plus the natural log of x plus 2 is equal to 4. So what we can do again, since these are both natural logs and there's a plus sign here, I can write that as a product. So this becomes the natural log of x times x plus 2 equals then this 4. Remember, the natural log has a base of b. So I can put this in exponential form, and this is going to be x times x plus 21, and that's going to be e to the power of 4. So from here, we have x squared plus 21x is equal to e to the power of 4. So this gives us then x squared plus 21x minus e to the power of 4. And that's going to equal then 0. So what in the world do we want to do with this equation?